Section 16.7, Surface Integrals. So, in this section, we're talking about a surface integral, which is just where we're integrating over some surface. Now, this surface is going to have the same domain. In this image, this domain happens to be a rectangle on the xy plane, but it doesn't have to be. We know that this domain can be a function in polar coordinates, it can be a function of x, it can be a function of y. We've already talked about the different ways that we can write these double integrals. Also, it can be lying on the yz plane or the zx plane. So we've talked about the different ways we can integrate, and all of this has been over a plane. Because the first thing that we do, if, say we want to find the volume, and let's just take, for example, the volume of this paraboloid that's capped at some z value. So maybe this will look something like this. We want to find the volume of this solid. All right, if we want to write a double integral, we're going to write this function, so f of x and y. So this is going to be our z equals something over this area. And what's this area? Well, generally this area is just the projection onto the xy plane. So to find this area, we would draw the xy plane. And in this case, if this was a paraboloid, well, a circular paraboloid, then the projection onto the xy plane would be this circle. And this is how we'd find our area. In this case, the difference is that this area is now a surface. And notice that we still have a domain that lies on the xy plane in this case. So our domain is going to be the same, but in this case we're integrating over a surface that is curved. And so the relationship between surface integrals and surface area is basically the same as between line integrals and arc length. This is also the same thing that we saw when we found the volume of a three-dimensional solid using triple integrals, where in the case where this function f of x, y, and z is equal to 1, the value of the surface integral is equal to the surface area. We remember with volume that when we use a triple integral to find the volume of a solid, that integrand, so what was inside of that integral, this function, must be 1. And so we find this formula, and you will be given this formula. There's no need to memorize this formula, that the double integral over some surface of a function in 3 variables is going to be equal to that same integral over the domain D of f of r of u and v. So all this is it's the parameterized version of this function. And so we have this function f of x, y, and z, and all we're doing is we're plugging in these parameters where x is a function of u and v. So this is going to look like f, where x is a function of u and v, y is a function of u and v, and z is a function of u and v, times the magnitude of the cross product of the partial derivative of u and the partial derivative, well, with respect to v, over that area. And so this might look a little bit familiar because we remember that the area of a surface when we had a parametric surface, it's just the double integral of the magnitude of that cross product of the partial derivative of r with respect to u and the partial derivative of r with respect to v over that area where this is our domain. And that's all we're saying on the last slide, is if f of r of u and v is equal to 1, so in this case we're really just saying that this function is equal to 1, then we get that surface area that we learned about last week. So now it's just like the the formula for surface area using that double integral, but now we just have an additional function inside of this integrand. So we're going to see some of the same techniques that we used last week. So let's do an example of this. We want to find the surface integral of x squared ds, where s is the unit sphere, x squared plus y squared plus z squared equals 1. And so we know that what we want to find is we want to find this double integral over this surface of f of r of u and v, where this is a vector, times the magnitude of the partial of r with respect to u cross partial of r with respect to v over that area. Notice that this x squared is not parameterized. This is just an x. If we write these parametric forms of that equation, it's going to be written in terms of u and v. We really said that u and v can be any two variables. Remember that. This doesn't necessarily represent just u and v. And we want our bounds to be in terms of this u and v. And we're talking about this sphere. So this is our first step. We want to parametrize or parametrize this surface S. And what's the best way to do that? Because we want to get this to be a function of two variables. Well, we know that this is a sphere, and so the best way would probably be with spherical coordinates. So because this is a sphere, we're going to use these spherical values to find r of some phi and theta. And here's why. I can write this because it's x squared plus y squared plus z squared equals 1. I know that my rho squared is equal to 1. And so my rho value is just 1 because I know rho is positive because it's the distance from the origin to any given point on this sphere. I also know that x is equal to rho, which is 1, times the sine of phi cosine theta. I know that y is equal to rho, which is again 1, times the sine of phi sine of theta. And I know z is equal to rho times the cosine of phi. And isn't this a parametric equation? I can write this as r of phi and theta being equal to sine of phi cosine of theta I plus sine of phi sine of theta j plus cosine of phi k. This will allow me to get this magnitude of the cross product of these partial derivatives. Because I can find the partial derivative in terms of phi, treating theta as a constant, this is just going to be, well, the derivative of sine of phi is cosine of phi. So this will be cosine of phi, cosine of theta I. Derivative of sine of phi, again, is cosine of phi. So this is going to be cosine phi, sine of theta, j. Derivative of cosine phi is negative sine of phi, k. With respect to theta, treating phi as a constant, this is going to look like negative sine of phi, sine of theta, I, plus sine of phi, cosine of theta, j. In terms of theta, this is just a constant, so plus 0k. And now we can write our cross product. And so this, and let's do the magnitude next, but this cross product of the partial with respect to phi cross partial with respect to theta is going to be, and let's draw this determinant here, so I, j, and k values, where I is just going to be cosine phi, cosine theta, or J is cosine phi, sine of theta, or K is negative sine of phi. Next line, our I is negative sine of phi, sine of theta. Our J is sine of phi, cosine theta, and our K is 0. And so this cross product is going to give us, well, our I term is going to be this times 0, which is 0, minus a negative, so plus sine of phi squared, cosine of theta, minus J times the quantity. Again, this will be 0. This will be minus a negative times a negative, so just minus sine of phi squared, sine of theta, plus K, and then our K term is going to be cosine phi, sine of phi, cosine of theta squared, minus a negative, so plus cosine phi, sine of phi, sine of theta squared. And I've already included that K. Okay, let's continue to simplify each term as much as we can. So the I term we can't simplify. That's just a sine of phi squared cosine theta. I. J term, we can just make this a positive sine of phi squared, sine of theta, J. The K term, what can we do with this? Well, I see a cosine phi, sine phi in both of these terms. So if I take that cosine of phi, sine of phi, and I factor out a cosine of theta squared plus a sine of theta squared, okay, well, cosine of theta squared plus sine of theta squared is just 1. And so in that K term, I am just left with the cosine of phi, sine of phi. And so now let's take the magnitude. So the magnitude of this cross product we just found is just going to be the square root, and I'm squaring all of these terms. So I've got the sine of phi to the 4th power cosine squared plus the sine of phi to the 4th power sine squared plus cosine of phi squared sine of phi squared. And I'm looking for that same Pythagorean identity. And I would encourage you to try to simplify this on your own and then speed up this video, because we did this before. We said that if we're looking for this Pythagorean identity, cos squared plus sine squared is 1. We've got a cosine squared. We've got a sine squared. And so I can call this the square root of the sine of phi to the 4th times cosine plus sine squared, which is 1. So this is just going to be sine of phi to the 4th for both of these two terms, plus cosine of phi squared, sine of phi squared. And the other thing I can do, let me see, I can factor out a sine of phi squared from both of these terms. And when I do that, I get a sine of phi squared plus a cosine of phi squared. And we see this identity happen again. I know the square root of sine of phi squared is just the sine of phi. And so this is the magnitude of these two partial derivatives, of the cross product of these two partial derivatives. This all boiled down to sine of phi. And please feel free to use this idea that if we want to take the cross product of the partial derivatives of the sphere, when we're talking about the parametrization of this sphere, this is just going to boil down to the sine of phi. So now looking back at our integral, we've got this part of the integral. The only thing we need left is f of this r of u and v, and then we also need our bounds. So let's talk about those. For our bounds, we need our bounds in terms of phi and in terms of theta, because everything's going to be parametric, right? So these are going to be our only two variables. We're writing everything in terms of phi and theta. And what are the bounds if we have this surface as a unit sphere? And we remember these bounds from when we talked about spherical integration. And we said, and we already proved this in that video for spherical integration, that phi is just going to go from 0 to pi, and theta is going to go from 0 to 2 pi. This is just so that we can take a circle. Essentially, we're picturing, if we're holding up kind of like a fan shape of a semicircle, and we're rotating this around one full rotation or 360 degrees, this sort of forms the volume of a sphere. That's where we got these bounds from. So these are going to be our bounds. Now let's put all of this together. And if we want to find, let's rewrite this integral. We said that our theta and our phi go from 0 to 2 pi and from 0 to pi. We still don't know what this parametrized form of that integrand is, but we said that this magnitude was just sine of phi. And these are our bounds for phi. These are our bounds for theta. Now our original integral had an integrand of x squared. So originally this was an x squared ds. And so how do we parametrize this? Well, we've got an x squared. Didn't we say that x is equal to rho, which is 1, times the sine of phi times the cosine of theta? Because this started off as x squared. This is going to turn into the sine of phi squared, cosine of theta squared. And so now we can say that our integral goes from 0 to 2 pi and from 0 to pi of the sine of phi squared, cosine theta squared, sine of phi, d phi, d theta. Okay. And this is the cosine, of theta. And so I've got two terms of sine of phi squared and sine of phi that are in terms of phi. I've got another term in terms of theta. And so let's split these up, because I know that 0 to 2 pi are my bounds for theta, and so this is going to be for the cosine of theta squared d theta. And I'm multiplying this by the integral from 0 to pi of, well, sine of phi squared times sine of phi squared is sine of phi cubed. d phi. Integrating these separately. On the left here, I see a cosine squared. I can't use u substitution. I can use this double angle identity though, that states that this is equal to the integral from 0 to 2 pi of 1/2 plus 1/2 cosine of 2 theta d theta, which is just equal to 1/2 theta. And what happens with this 2 theta in here? Well, we said that we could use substitution, but we know this is really going to multiply this term by 1/2. So this is going to be 1/2 theta plus 1/4 times the cosine of 2 theta as we go from 0 to 2 pi. When I plug in 2 pi to 1/2, I'm left with pi. Plug in 2 pi to 1/4 cosine of 2 theta. This becomes the cosine of 4 pi, which is 1. And so I get pi plus 1/4 minus 0, and cosine of 0 is 1. And so I get 0 plus 1/4. And so this is just going to leave us with pi. On this integral, what can I do to find the sine of phi cubed? And we remember back from Calculus 2, well, we can take a sine of phi out of here, and we can rewrite this as the integral from 0 to pi of the sine of phi squared times the sine of phi d phi. Because in this way, if I have a sine of phi squared, I can rewrite this in terms of cosine, and then I can use that u substitution. And so if I write this in terms of cosine, I have the integral from 0 to pi. I can call this, because I know that Pythagorean identity, I can call this 1 minus the cosine of phi squared times the sine of phi d phi. Because now if I allow u to be equal to the cosine of phi, then my du, derivative of cosine, is negative sine of phi d phi. And I can rewrite this as the integral. If I pull out a negative, this becomes the integral of 1 minus u squared du. Everything's in terms of u, not too difficult to evaluate. This just becomes a negative, and we've got the integral of 1 in terms of u, which is u, minus 1/3 u cubed, which is a negative, and now this is going to be cosine of phi minus 1/3 of the cosine of phi cubed as we go from 0 to pi. And this will look like a negative. Cosine of pi is -1. Again, cosine of pi is -1. When we cube a -1, it's still a negative, and so we're adding 1/3 times 1, which is 1/3. And then we're subtracting from that a negative, which makes this a positive. Cosine of 0, which is 1, minus 1/3. And this gives us a negative -1 plus 1, so 2. And this gives us a negative 1/3 minus 1/3, so 2 minus 2/3, which is 4/3. And finally, pi times 4/3 just becomes 4 pi over 3. And I know this was a long problem, but now we can use this idea that when we're taking the cross product of these partial derivatives, where this surface is a unit sphere, we know that's just going to give us the sine of phi. We can expand this to ideas where this sphere has a rho, or in other words, a radius of something greater than 1, and we're going to talk about that in a later problem. So let's do one more example that is not as painstaking. And it looks like we're actually going to use that idea right now, because example 2 asks us to evaluate this double integral over the surface of z ds, where s is the upper half of a sphere of radius 2. Now I know that the upper half of a sphere of radius 2 looks like x squared plus y squared plus z squared is less than or equal to 2 squared, which is 4. And I also know that I have the restriction that z is greater than or equal to 0, just because this is the upper half of that sphere. Doesn't this look a whole lot like the unit sphere? Now, I'll have that restriction of the upper half. However, remember what we did with the unit sphere, because our goal is to get this in a form where we can take the double integral over the surface where we've parametrized this integrand, so we're going to call that f of r of u and v, times the magnitude of the partial derivative with respect to u, cross partial derivative with respect to v, dA. So this is our goal. And the most difficult part of this was to find the magnitude of this cross product. Now our surface, and again this is based on our surface isn't much different here. And so what we're going to do is let's just copy and paste everything that we did from example 1 as far as this cross product went, and let's look at that. And so let's see, let's just copy down all of this, and we can paste it here. Let's just paste it as a picture. Great. All right, let's shrink this down a little bit. This is what we did in the last problem. Just kind of put this off over to the side. Now let's notice our only difference here. Look at this rho. We know that the rho squared is equal to 4, and we're actually given that because this is the radius of a sphere, in this case our rho is going to be equal to 2 rather than 1. And so what's that going to change? Well, that means we'll have a coefficient of 2 in our x, y, and z terms, because remember this is rho sine of phi cosine theta, and likewise with the others. And so this is going to change, let's see, it's going to change all of these partial derivatives, because remember what happens when we have any kind of coefficient. When we take that partial derivative, the coefficient is just sort of along for the ride. And so all of these terms are going to now have coefficients of 2. These are coefficients. I'm just kind of putting them above because there's no space. All right, so we're going to have coefficients over here. Well, this is just a 0, so this one doesn't really change. And then what's going to happen when we take this cross product? Again, everything's got a coefficient of 2. And now we've taken that cross product and we have, for example, let's look at our I term. We've got a 0 minus a negative, so plus 2 sine phi times 2 sine phi cosine theta. Well, this becomes a 4. And because we have a 2 in front of everything here, all of these terms are going to become a 4, have a coefficient of a 4. And so when we simplify, not really much changes here, because for example, right here, when we factor out this cosine phi sine of phi, again, this just has a 4 attached to it. Okay, so all of these become 4s. And then what happens when we take the magnitude? Well, we're squaring all of these terms. And so this is going to be a 16, 16, 16. And finally, when we'll be left with that this is factoring out a 16 from everything. When we take the square root of 16, we know that's going to be a 4. And so this will allow me to conclude that the cross product of r sub u cross r sub v, I'm going to call this phi, and theta. And that's because I know that S is the upper half of a sphere, and so I'll use these spherical coordinates here. This is just going to be 4 sine of phi. And this all just comes from example 1. And now, so what's our grand conclusion? Our grand conclusion is that if we want to find this cross product, the magnitude of this cross product of a sphere, a radius of 2 just gets squared. And so this becomes a 4 in front of our sine of phi. You can absolutely use this for problems on the test, problems in your homework. You don't have to go through all of this because this is always going to be true, and you're going to kind of see this a lot because a sphere is a common surface of integration. And so now that we've got this, the rest of the problem is relatively simple. Well, we know that z is just equal to rho, which is now 2, times the cosine of phi. And so we just have the double integral. And let's talk about our bounds really quickly, because now we have half of a sphere, and so got something that looks like this. We know that our our phi is going to be this angle. This is our phi. And we know that this phi only goes from 0 to pi over 2. If it went from 0 to pi, that would be our whole circle, but this only goes from 0 to pi over 2. So our new bounds, 0 to pi over 2, and theta is still going to be 1 revolution, so that's still going to go from 0 to 2 pi. Let's just kind of make a distinction with this, just for our notes, so no one is terribly confused that this all comes from the first problem and everything outside of it is for this problem. Okay. And so now back to our problem. We know that our bounds for phi go from 0 to pi over 2. Our bounds for theta go from 0 to 2 pi. Inside we've got 2 cosine phi times 4 sine of phi, d theta, d phi. And now I don't see anything with a theta inside of it, and so I can break this up. Let's break this up into 0 to 2 pi of d theta. So that's really just a 1 d theta times the integral from 0 to pi over 2. Well, if I simplify, this becomes 8 cosine of phi sine of phi d phi. On the left-hand side, I know this is just going to give us a 2 pi. We've seen this integral enough. On the right-hand side, I've got a cosine, I've got a sine. Because I know the derivative of sine is cosine, if I want to avoid negatives, I can let u be equal to sine of phi, which would mean our du is equal to cosine of phi d phi. And so I can rewrite this integral. Let's pull this 8 out to the front as 8 times the integral of u du. The integral of u, antiderivative of u, is going to be 1/2 u squared, and so I can call this 4 u squared, which is equal to 4 times the sine of phi squared, as we take this from 0 to pi over 2. And the sine of pi over 2, I know is just 1. The sine of 0 is 0. And so this leaves us with 4 minus 0. Finally, because I'm multiplying the values from both of these integrals, 2 pi times 4 is equal to 8 pi. And so we've evaluated that integral. Much less painful when we don't have to derive that magnitude of that cross product in spherical coordinates. So in the special case that we have some surface and the equation can be written in the form of z is equal to g of x and y, this can be called a parametric surface with these equations. We remember that when we find a parametric surface, when we parameterize or parametrize this surface, all we're saying is that, okay, we know that z is a function of x and y, and if we've written z as a function of x and y, and we just want x and y in terms of x and y, then x will just be equal to x and y will just be equal to y. And we talked about this idea when we introduced parametric surfaces. You saw this. Sometimes x was equal to x, y was equal to y, and sometimes z is equal to z. And if this is true, when I want to find the partial derivative of this surface with respect to x, then for my I component, I'm looking at the derivative of x with respect to x, which I know is just 1. The derivative of y with respect to x, well, this is just a constant in this case, and so that's going to be 0, so this is plus 0j. And then the derivative of z with respect to x is just going to be the derivative of this function, which is why we have the partial of g with respect to x. That's our k component, so just the derivative of this with respect to x. Same idea with the y here. So we get these two equations. Now when we take the cross product of these, we get some simplification. And a lot of that simplification comes from the idea that in the partial with respect to x, we don't have a j term. In the partial with respect to y, we don't have an I term. So that's how we can get such a simple cross product. And once we have that, we can then take the magnitude, and we come to this conclusion that in the case where z is a function of x and y, this cross product, which remember in the last two problems was the most difficult part of this, is just going to be the partial with respect to z, this magnitude of the partial with respect to x squared plus the partial with respect to y squared plus 1. So this is going to be our new cross product. So in this case, this is easier because we don't actually have to take the cross product. This skips the step of the cross product for us. And also you will be given this formula as well. And the other thing we need to do here is that if we looked at the parametric equations, where in this case x and y were our two parameters here, then we also needed to parameterize this function. And so we've replaced z with g of x and y, so that this was just a function of x and y as well. Because we remember what parametric equations do. In the case where we had two dimensions, we could write everything in terms of t, right? So when we had x and y values, we could write them in terms of t. We essentially went from two variables to one variable. In this case, everything gets simplified because again, now inside of this integral, we went from 3 variables, x, y, and z, to only 2 variables. We can call those 2 variables u and v. We can call them phi and theta. We can call them x and y. As long as we have 2 variables, we've made our process a whole lot easier. That is how we can eliminate the cross product, because we know a cross product is 3 by 3, so where we have 3 variables with each. Okay. One thing to note here is that this isn't necessarily true if we can write z as a function of x and y. If we can write y as a function of x and z, or x as a function of y and z, then the same thing applies. So it doesn't necessarily have to be that we can write this as z equals, we can write this as x equals something, or y equals something. This idea will work as well. So let's go for an example. Example 3, we want to evaluate this double integral of y ds, where s is the surface, z is equal to x plus y squared, where x goes from 0 to 1 and y goes from 0 to 2. And so first question, is this a function, is z a function of some x and y? And yes, we have z equals, we've got x and y's on the right hand side, great. In this case, we're already given our domain. We're told that x goes from 0 to 1 and y goes from 0 to 2. And when we think about what type of domain this is, because this is our domain D, this ends up just being a rectangle. And so we've actually got the surface graphed for you here, so you can see that x going from 0 to 1 and y going from 0 to 2, I'll try my best to draw this to scale, is going to give us a domain of something like this, where this is the region lying on the xy plane, and this is our domain D. We can see that rectangular domain. So we've already got our bounds. The only other thing we need to do is we need to deal with this ds. This ds tells us that this is a surface integral, and in this case our ds, rather than being the cross product, and let's make sure this s is capitalized for consistent notation, this is going to be equal to the square root of the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared plus 1. So let's find this. This is equal to, well, the partial of z with respect to x, just the derivative of x, is just 1. So this is going to be 1 squared plus the partial derivative of z with respect to y. Well, the derivative of y squared with respect to y is 2y. So that'll be 2y squared plus 1. Okay, and we can call this a 4y squared plus 1 plus 1. So I'm going to call that the square root of 4y squared plus 2. That's our ds. And so now we can rewrite this integral. Now, is y in terms of x and y? Kind of a weird question, but yes, it is. We don't have any z's in here. Y is in terms of x and y, and so we can leave that y as is. So I can leave that y as is. I'm adding my ds of 4y squared plus 2. And I know my bounds go from x being from 0 to 1 and y going from 0 to 2. All right. Now, because both of my bounds are constants, that just comes from a domain that is a rectangle, I don't see any x's inside of this integral. My integrand is completely in terms of y, and so I can split this up. Let's pull off my integral for the x's going from 0 to 1. So that's just going to be 0 to 1 dx times the integral from 0 to 2 of y times the square root of 4y squared plus 2 dy. Over on the left here, taking the integral of 1, the antiderivative of 1 is just x. X going from 0 to 1 is just going to give us 1. On the right-hand side, we've seen this pattern a lot, so we might notice that while we can't integrate this, this is a great candidate for u substitution. My issue is what's going on inside of the square root, and I'm going to allow u to be equal to 4y squared plus 2, leaving me with a du, the derivative of 4y squared plus 2, of 8y dy. And so I'll pull a 1/8 outside of that integral. This is going to look like u to the power of 1/2 the square root of u du. Taking that integral, that antiderivative, that's going to be 1/8 times 2/3 u to the power of 3/2, which is going to be 2 over 24, which is 1/12. And I know my u is going to be 4y squared plus 2 to the power of 3/2, and our bounds go from 0 to 2. And this will be equal to 1/12 times, when I plug in a 2, I get 4 times 4 plus 2, so I get 18 to the power of 3/2, and I'm going to call that 18 root 18. When I plug in a 0, I get 2 to the power of 3/2, so 18 root 18 minus 2 root 2. 2 to the power of 3/2. And so this would be my final answer, but let's see if we can clean this up a little bit. Because we've got two different square roots, and if we have something that looks like this, we may not be able to clean it up. But in this case, I'm going to just ask myself, can this be simplified? Just because we haven't worked on simplifying square roots in a little while. And I'm thinking, can I break up the square root of 18 into a perfect square and a non-perfect square? Because I know it's not a perfect square itself, but I can break this up into root 9 and root 2, and so 18 is 3 root 2. And because I'm multiplying 3 root 2 by 18, I've got 18 times 3 root 2 minus 2 root 2. And so 18 times 3 is 54, so I've got 54 root 2 minus 2 root 2, which is 52 root 2. Finally, calling this 1/12 times 52 root 2. Well, 52 divided by 12, let's see, I can take a 4 out of both of these. 52 divided by 4 leaves us with 13. And so we're left with 13 root 2 over 3. This is our most simplified answer. And while we talked about the idea that if we have insanely large square roots, there's no need to simplify, if we can simplify fairly easily, it's always a good thing to do just because this answer looks a lot cleaner. And let's do one more example of this. Example 4, evaluate the double integral over that surface of 6xy, where S is the portion of the plane x plus y plus z equals 1 that lies in the first octant. So let's sketch this out. We know this is going to be that three-dimensional surface. We know that x plus y plus z equals 1. Now, if we forget, we can always just plug in a 0 and a 0 for two of the variables to find these intercepts of the axes. But I know that this is just going to have intercepts of 0, 0, 1, 0, 1, 0, and 1, 0, 0. And so my surface is going to look something like this. So this is going to be that surface. Now, to use this idea from before, because I want to avoid a cross product where I can, I know that I can write this in the form of x equals something, y equals something, or z equals something. And it doesn't really matter which. Now I'm going to choose z equals 1 minus x minus y, and I'm going to tell you why. Because inside of this integrand, I see an x and I see a y. If I were to redefine x in terms of y and z, then I would have to write that equation, really that expression, inside of this integrand. So it would just make my integrand a little bit more complicated. So that's why I'm going to choose, if I don't have any other restrictions on this, I'm going to choose z. All right. Now, I want to find the bounds of this surface, and I'm going to do this like any other integral. Because I have z equals something, then I can look at the xy plane. And I'm just going to draw these positive x and y values because I know that this lies in the first octant. And where z is equal to 0, I know x plus y equals 1. And so x plus y equals 1 has intercepts of 1 and 1. And so it's going to be this triangle. And so my bounds, I can draw a vertical arrow, so this is going to be y equals something. I know I can write this as y equals 1 minus x. And so I can write my bounds as x and y, where y goes from 0 to 1 minus x, and x just goes from 0 to 1. I know all of these intersections are just 1. So I've got my bounds. The only other thing I need to do is I need to find this ds, which is the square root of the partial derivative of z with respect to x. Well, that's just going to be a -1. The partial derivative of z with respect to y is going to also be a -1. And so I've got -1 squared plus -1 squared plus 1, which is just going to be the square root of 3. So that's our ds. And so we can write this double integral where x goes from 0 to 1 and y goes from 0 to 1 minus x. Notice that I can no longer split this up into integrals where I have an integrand of a function of x and a function of y, because now my y bounds are a function of x. And I've got a 6xy root 3 dy dx. Let me just rewrite this, and I'm going to put this 6 root 3 outside of the integral so we don't have to worry about it. Rewriting this as the integral from 0 to 1 and 0 to 1 minus x of xy dy dx. Antiderivative of xy with respect to y is going to be 1/2 xy squared, as y goes from 0 to 1 minus x, which is going to be 1/2 times the quantity, or let's leave out that x, because x is a constant in this case, 1/2 x times the quantity of 1 minus x squared, which is 1 minus 2x plus x squared, minus 0, which is going to be a 0. And so this will give us the integral from 0 to 1 of 6 root 3 times this integral of 1/2 x minus x squared plus x squared times 1/2 x, so plus 1/2 x cubed dx. And this will give us 6 root 3 times the quantity. The antiderivative of 1/2 x is 1/4 x squared. Negative x squared turns into negative 1/3 x cubed. 1/2 x cubed turns into a 1/8 x to the 4th power. Taking that from 0 to 1, this is just going to give us 6 root 3 times 1/4 minus 1/3 plus 1/8. And so this ends up giving us, let's see, 6 over 24 minus 8 over 24, that's a negative 2 over 24 plus 3 over 24. And so I get 1 over 24 times 6 root 3. 6 root 3 over 24 is equal to root 3 over 4. You could also just kind of do this in a calculator. And there we have it. We've evaluated that integral. So now for piecewise functions. So if S is a piecewise smooth surface, which means that it has a series of smooth surfaces that are connected, that intersect only along specific boundaries, then the surface integral can be defined by this idea that all we're doing is we're adding together these different surface integrals over the surfaces. We can have an infinite number of surfaces that are connected. And this is the same kind of idea as when we talked about taking line integrals that are a piecewise smooth curve, where we can just break this up into each of its smooth curves. In this case, we have smooth surfaces, and just integrate separately. And so let's do an example of this. Example 5, we want to evaluate this double integral of z ds, meaning it's a surface integral where s is the surface whose sides s1 are given by the cylinder x squared plus y squared equals 1, whose bottom surface is the disk x squared plus y squared is less than or equal to 1 in the plane z equals 0, and whose top surface is part of the plane z equals 1 plus x that lies above S2. So we have an image of what this might look like. If you weren't given an image, in this case, it might be a great idea to use Mathematica to graph this. And because we have these 3 different surfaces, each of these surfaces is smooth, and each of these surfaces is connected. So we've got the first surface of this cylinder, and so we're going to break this up into the double integral over S1 of z ds plus the double integral over the region of S2, which is underneath of this cylinder. It's the circle that lies on the xy plane. S2 of z ds plus that double integral over S3, which is just the top of this cylinder, the plane z equals 1 plus x of z ds. So we're just breaking this up. Now the most difficult part of this is going to be to find out what the boundaries and this ds of each surface are. Because we remember that when we have this ds, this is going to come from 2 things. So ds is either the magnitude of the partial derivative of r with respect to u cross partial derivative with respect to v, or in a special case, it's the square root of the partial of some z with respect to x squared plus the partial of z with respect to y squared plus 1. Where this is the special case when we have some z is equal to a g of xy. And of course, we said that this can be an x equals or y equals. But either way, we've got our ds from either one of these 2 different expressions here. We also need to find our bounds, which get a little bit strange when we have multiple surfaces. And so let's start with S1. So for S1 is our cylinder x squared plus y squared equals 1. Now, because this is a cylinder, the best way to categorize this and to find our bounds are by using cylindrical coordinates. Now, because we can't write this as a function of x or y, we're going to use this first form of ds. So we're going to parameterize this. And so the parametrization will give us an x that is equal to the cosine of theta, or I should really say r cosine of theta, where r is 1. A y that's equal to r sine of theta, and a z that's just equal to z. And so I can find those partial derivatives, and before I do that, I can write this as a function of theta and z, where cosine of theta is the I component, sine of theta is the j component, and z is the k component. Now I can find those partial derivatives with respect to theta, giving us, and I'll just write it in this vector form, with respect to theta, the partial derivative is going to be derivative of cosine is negative sine, so negative sine of theta. Derivative of sine is positive cosine, so cosine of theta. And with respect to theta, z is a constant, so that derivative is going to be 0. Then we have the partial derivative with respect to z. Because these are a vector, I know we can kind of get a little bit lazy with the notation. I just want to make sure I'm being consistent here. Because these are vectors, the partial with respect to z is just equal to treating theta as a constant, waiting for this file to save. Both my x and y terms are going to be 0. The derivative of z is just 1. And so we can already see that this is probably going to simplify that cross product a good bit. So we can find that cross product of those two vectors by setting up that determinant of I, j, and k, where we have negative sine of theta, cosine of theta, 0, and then we've got 0, 0, 1. This is going to give us an I component of cosine of theta minus 0, minus a j component of negative sine of theta, plus a k component of 0 minus 0. And so this will just give us cosine of theta I plus sine of theta j. Remember that this is our cross product, and so when we find the magnitude of this cross product, we're just taking the square root of both of these terms squared. So the cosine of theta squared plus the sine of theta squared. And we can see what happens. We know that this is just equal to 1, and the square root of 1, because we know this needs to be positive, is just 1. And so now for the issue of our bounds. Now, we found that this can be written as a function of theta and z. And so our bounds are going to be in terms of theta and z, unless we rearrange this. All right, so what I'm looking at, and I can just look at this version of the graph. In terms of theta and z, well, I'm looking at this surface 1, so the outside of this cylinder. This cylinder makes its way all the way around the origin here. So I can say that theta goes from 0 to 2 pi. And what about z? Well, how can I measure the bounds for z? Well, because the cylinder starts on the xy plane, I know that my z values are all going to start at 0. And then if I were to draw just a sample arrow, we know that this starts at 0, but where does it finish? How can we categorize this z value, this changing z value? Well, this is bounded on the top by the equation z equals 1 plus x. And so we can see that z is going to go from 0 to 1 plus x. However, there's one problem with this, and that's that we want this in terms of theta and z and not x. But because we parametrized this, we said that x is equal to the cosine of theta. And so we can just replace this x with a cosine of theta. And so our z is going to go from 0 to 1 plus cosine of theta. And so we've got everything that we need. And so we can set up this double integral going from 0 to 2 pi and from 0 to 1 plus cosine of theta. Remember, everything needs to be in terms of z and theta. Because we just have a z inside of this integral, that can stay as is. So this is just going to be a z. We are going to multiply this by our ds, which is 1 dz d theta. And we know we're going to add these together, so let's save this actual integration for the end. But our next step is to deal with S2. So let's talk about S2. And we were given in the problem that S2 is the disk x squared plus y squared is less than or equal to 1. In the plane z is equal to 0. And so if this lies in the plane z equals 0, what that means is that as far as z goes, my equation is always going to be z equals 0. Because I have this double integral over this surface, so this is what we're saying, this surface is x squared plus y squared is less than or equal to 1. However, this function inside of the integral is just 0. So no matter what we have for this surface, if z is always just equal to 0, then whatever we get, this integral is just going to be equal to 0. And this is just, and so we don't even have to worry about anything else. Because this surface, S2, because it lies on the plane z equals 0, and our integrand is just z, this is always going to be equal to 0. And again, this is just a little bit abstract, but if we can think of this double integral as, say, a volume with a height of 0, so the volume of an object with a height of 0. Well, I understand that that's not exactly what this is, but it's kind of the best way to picture what's happening here. So we don't have to worry about S2. Remember, it's not just surface area. We would just be talking about the surface area of this thing if and only if this integrand was 1, right? So if instead of z, this was just a 1, then we would be talking about the surface area, and then the bottom of this would have some area, right? It'd just be the area of this circle on the bottom here. But that's not what's happening because we've got a z in that integral, again, making this a little bit more abstract. So now for our third surface. So we're talking about this double integral over S3. And this is going to be the top part of this. And let's just copy and paste this onto a new page for reference. And S3 is given by this equation, z equals 1 plus x, so on the top of this solid. So z equals 1 plus x. We know we need to find this ds. And isn't this one of the special cases? Because isn't this really z as a function of x and y? And so rather than doing this cross product that we did with the first surface, we can just use that shortcut. And we know that ds is just the magnitude of, so the square root of the partial of z with respect to x squared plus the partial of z with respect to y squared plus 1, which in this case, partial with respect to x is just going to be a 1. That'll be a 1 squared plus. The partial with respect to y, I don't see any y, so this will just be a 0. And then plus 1, giving us a ds of the square root of 2. And so now that we have this ds, we need to talk about our bounds. All right. Now because this is a function of x and y, we want our bounds to be in terms of x and y, right? Because we wrote this as a function of x and y. If we want our bounds in terms of x and y, then what I'm going to look for is I'm going to see what's happening along the xy plane. Along the xy plane, this upper surface, although this is a plane, it's still bounded by this cylinder, x squared plus y squared equals 1. So if we were to look at this from above, the view we would see, the projection onto the xy plane, would look like a circle with a radius of 1. Circle is going to be x squared plus y squared is equal to 1. Now it gets a little bit funky here because we know that if we set up these bounds in terms of x and y, it would get a little bit weird. We'd have some negative square root of, for x, for example, 1 minus y squared, to positive square root of 1 minus y squared. We know that the best way to describe this is just using polar coordinates. So we're going to switch to polar since our bounds on the xy plane are a circle. And in polar coordinates, this makes our lives a little bit easier. We know our r just goes from 0 to 1, and our theta just goes from 0 to 2 pi. And so we have this integral, this double integral from 0 to 2 pi and from 0 to 1. Our integrand is still z. And because our integrand is z, and we want to switch that to polar coordinates, well, we know that z is 1 plus x. And we know that x in polar coordinates is really r times the cosine of theta. So because this is a z, times ds, which is root 2, d r d theta. Again, we can really rewrite this as 0 to 2 pi, and I'm sorry, I forgot that r in there, it's very important. 0 to 2 pi, and from 0 to 1 of z, which is 1 plus x, root 2, r dr d theta. Finally, our x is r cosine of theta. So that's going to be 1 plus r cosine of theta times root 2 times r dr d theta. And this is our integral for S3. Okay, now let's actually integrate both of these. And I'm just going to pull the integral from the previous page. And we've got the second integral here. And now we can evaluate. And so this is going to be, let's start over here. This z, starting with the inside, is going to turn into 1/2 z squared as z goes from 0 to 1 plus the cosine of theta, which is going to turn into 1/2 times 1 plus 2 cosine theta plus the cosine of theta squared. So let's pull out the 1/2. We're going to get a 1/2 times the integral from 0 to 2 pi of 1 plus 2 cosine theta. And because I know I can't integrate this cosine of theta squared, I'm just going to use this double angle identity and call this plus 1/2 plus 1/2 cosine of 2 theta. We've seen this identity enough. D theta. Finally, this is going to be a 1/2 times the quantity 1 plus 1/2 turns into a 3/2 theta plus 2 sine of theta. I know that this 2 theta on the inside of the cosine function is going to leave us with a 1/4 sine of 2 theta as we go from 0 to 2 pi. And this will give us 3/2 times theta. Theta is 2 pi, and so this is going to be 3 pi times 1/2. We know that the sine of 2 pi, the sine of 4 pi, the sine of 0, and again the sine of 0, all of this is going to be 0, and so this is just going to give us 3 pi over 2. And so let's add that to what we get over here for this third surface. So if I simplify this, I can bring the root 2 out front, I can be left with, and I'll distribute this r, I'll be left with an r plus r squared cosine theta dr d theta. When I take that antiderivative with respect to r, I am left with 1/2 r squared plus 1/3 r cubed cosine theta, plugging in 0 and 1 to r, and I get that this is equal to the square root of 2 times the integral from 0 to 2 pi. This is going to give us 1/2 times 1, so 1/2 plus 1/3 times 1 cosine of theta d theta. And finally, this will give us root 2 times the quantity 1/2 theta plus 1/3 sine of theta as we go from 0 to 2 pi. When I plug in 2 pi to 1/2, I just get to 1/2 theta, I just get pi. So this is going to be root 2 times pi. I know that the sine of 2 pi and of 0 is just 0, and so I'm just left with root 2 pi. Finally, my last step is to add both of these. And so I'm just adding these two values. I'm adding 3 pi over 2 plus root 2 pi. And the best thing we can probably do is just to factor out that pi, and we're left with 3/2 plus root 2. And this is our final answer. Just 3/2 plus root 2 times pi. Let's just erase these so we know that those aren't our final answers. Okay, and that is it. Yes, these piecewise smooth curves get a little bit messy just because we have multiple integrals. But the point is that we can integrate all the same. We're using the same ideas, just with multiple different surfaces. So now for oriented surfaces. This might look like a lot, but you actually already know most of this. Because we know that if we have some surface, as long as this is a smooth surface, then at any point along this surface, let's say this point right here, I can find a tangent plane. So at this point, I can find the partial derivatives with respect to x and y that make up this tangent plane. We talked about this in one of the previous units, where this is the tangent plane. Also at that point, we can find a normal vector, and we know that normal vector just has an angle of 90 degrees to this plane. And this gives us two normal vectors. It gives us a normal vector pointing upward and outward, and it gives us a normal vector pointing downward. Because if we have a plane, there are just two different directions that we can have this normal vector. And that's why, if we remember, when we found normal vectors kind of at the beginning of this course, we said that if all of your signs flipped, it was all okay. Didn't matter, because we've got two normal vectors. And so if we find a unit normal vector, and remember, unit just means it has a length of 1. To unit normal vectors, it has a magnitude of 1, so it's a normal vector with a length of 1. We can find a normal vector at any point on this surface, and we can call this an oriented surface. Now we've got two orientations. We've got n pointing upward and we've got n pointing inward. And we know how to find n because we know that, back to this example, if we wanted to find that normal vector to the plane, we're just taking the cross product of the partial with respect to x. So the partial of this vector with respect to x and the cross product of the partial with respect to y. And that's going to give us this normal vector. And so that's where we get this definition. Just dividing by that magnitude gives us the unit normal vector. here's the new bit of information here. For a closed surface, a positive orientation is the one for which the normal vectors point outward from E. So if we have some closed surface, just means essentially like a shape, then the positive orientation is going to be n pointing outwards. If we have inward pointing vectors, this is a negative orientation, and we can sometimes call that a negative n. Now this is only important to understand this next idea of surface integrals of vector fields. And so now we have this example, and this part gets a little bit confusing, mostly because in this class we don't really dive into the physics aspects of it, so if we kind of lost you with this part, that's okay. But to make sense of this, let's suppose that we've got a fishing net. Let's suppose this is a fishing net. And we want to find the water particles that pass through this fishing net in a certain period of time. Well, we can find the rate of this flow per unit area given by rho times v, where rho is just the density of this fluid and v is the velocity of this fluid. Now, this v is capitalized, it's a vector, because at different points in this stream, the velocity can be going in different directions, right? We can have a current that blows this way and then this way underwater. So the velocity doesn't necessarily need to be constant, and so we can represent that with a vector. Well, we can divide the surface into a series of small patches, and we can essentially find the mass of fluid per unit time using the quantity of the dot product of rho, v, and n of this area. Now, why do we use the dot product? Because we remember the dot product essentially tells us the rate at which these two vectors are facing in the same direction. So it's sort of the projection of one vector onto another. Now, again with this example, if I can picture that I have a particle underneath of this net, right? A particle of water underneath of this net. And I have some velocity and it's really a vector field of this water, that this water's moving. Won't this particle move the quickest through the net if the velocity of the water current is pointing in the exact same direction as the normal vector to this surface? If I have a water particle and the velocity is pushing it this way, which is perpendicular from the net, remember what the dot product of two perpendicular vectors are? It's 0. If I have a water particle that's being pushed perpendicular to the normal on this net, it's being pushed parallel to this net and it won't push through. I think that's the best way that we might be able to describe this. And I know it gets a little bit more complicated than that, but that's our general idea. And so that's how we get to use the dot product. And we showed a little bit of this. You could see in 2 dimensions when we talked about the line integral of a vector field. This is just the surface integral of a vector field. And so this is how we get that the flux integral, which is just the surface integral for a vector field, is going to be this vector. Remember that a capital F is our vector field with the dot product of the n, which is our unit normal vector. This is going to be our surface integral. We can also call that flux. And so this brings us to the definition that if F is a continuous vector field defined on some surface with a unit normal vector n, then the surface integral of F over S is just equal to the integral of the dot product of F and n with that ds to show us that this is indeed a surface integral, and this is called the flux. And one more thing we're doing is that we know that ds, remember that ds is equal to the magnitude of the partial derivative with respect to u cross partial derivative with respect to v, right? So when we plug that into this formula, these magnitudes cross each other out, and that's how we got rid of the magnitude to get to this formula, which is the one we're actually going to use of flux, which is the double integral of f, the vector field, and the cross product of these partial derivatives. And so you'll be given this formula for flux. So let's use it. Example 6. Find the flux of the vector field f of xyz equals zi plus yj plus xk across this unit sphere. And we know that if we want to find the flux, we're looking for the double integral over the region D of the dot product of the vector field f and the cross product of the partial derivatives of that vector over that area. And so if I want to start with this cross product because that's often kind of the most tedious part of this. And when I'm talking about this unit sphere, we said that the best way to parametrize this, surface, in this case would be with spherical coordinates. And so I'm going to let x be equal to rho, which is 1, times the sine of phi cosine of theta. I'm going to let y be equal to rho, which is 1 times the sine of phi sine of theta, and z can be equal to rho cosine of phi. So I've got the parametrization of this unit sphere. And so when I find this cross product, I'm really talking about the cross product of this partial derivative with respect to phi with the partial derivative with respect to theta. And we used a unit sphere. In fact, we used this in number 1. And so I'm just going to take this from example 1. And from example 1, we found this to be, let's go look back and look at that example. Okay, from example 1, we found this cross product and we simplified it to be this. Sine of phi squared cosine theta I plus sine of phi squared sine theta j cosine phi sine phi k. Let's see if we can remember that. All right, and this is going to be the sine of phi squared cosine of theta I plus the sine of phi squared sine of theta j plus sine of phi cosine of phi k. Okay, so we've already got this cross product. Now we just need the dot product with f. Now notice that this is parametrized. We have everything in terms of phi and theta, and so we're going to need to do the same thing with this f. And so if we want to find f of r of phi and theta, all we're doing is we're plugging this x, y, and z into this function. And so I've got zi, well that's going to make this a cosine of phi I. I've got yj, that's going to make this a plus sine of phi sine of theta j. I've got an xk, and so that's going to make that a sine of phi cosine of theta k. Next, I'm going to take that dot product. So I'm going to simplify all of this before creating this integral. So when I take this dot product of f of r of phi and theta. And the cross product that we just found well, this is just equal to. And all I'm doing is, and this would be kind of a pain to write out, and so I'm not even going to write this all out. I just know that this is going to be a scalar. I know that I'm multiplying each component and adding all of these together. So I've got the sine of phi squared cosine theta times cosine phi. Well, that's going to give me the sine of phi squared cosine phi cosine theta plus the sine of phi squared sine theta times sine phi sine theta. So that's going to look like the sine of phi cubed sine of theta squared plus sine phi cosine phi times sine phi cosine theta. So again, that's going to be a sine of phi squared cosine of phi cosine of theta. And I'm looking to see if there's any way I can simplify this. And I see two of these terms. I see two of these sine of phi squared cosine phi cosine thetas. And so I can combine these to call this a 2 sine of phi squared cosine of phi cosine of theta plus sine of phi cubed sine of theta squared. Okay, so this is our dot product. Now let's talk about our boundaries. And for our bounds, we want these in terms of phi and theta, because all of this is parametrized. And so if we're talking about this unit sphere, we're going to see these standard bounds. So this just tells us that phi is going to be equal to the interval from 0 to pi. Theta is going to go from 0 to 2 pi. And we've already proved this a couple times, so I won't go through that too much. And so let's set up this double integral. So this is going to be the double integral as phi goes from 0 to pi, and as theta goes from 0 to 2 pi, of 2 sine of phi squared cosine of phi cosine of theta plus sine of phi cubed sine of theta squared d theta d phi. Notice that we don't have a ds, and that's because we're already given in this formula that flux is the double integral with respect to an area. If we have this ds, then we're going to need the magnitude of that cross product or our shortcut for those special cases that we talked about, but we turned this into a typical double integral. This is no longer an integral over a surface because we don't have that ds. And so essentially what that means is that we can just solve this normally. Now because I see a plus in both of these terms, have a lot going on, I'm going to separate this into two different sets of integrals. And so this is going to be the double integral from 0 to pi and from 0 to 2 pi of 2, and I can pull out this 2, times the sine of phi squared cosine of phi cosine of theta d theta d phi plus the double integral with the same bounds from 0 to pi and from 0 to 2 pi of the sine of phi cubed sine of theta squared. Again, same bounds, d theta d phi. Over on the left-hand side, this is going to be really messy if I try to integrate this with respect to theta and then with respect to phi. But I can break this up into everything with a theta and everything with a phi. And so I'm going to take this 2, I'm just going to leave it on the outside so I don't have to worry about that. And I'll start with this theta because that's a little bit more simple. So from 0 to 2 pi, I've got a cosine of theta d theta, and I'm multiplying that by the integral from 0 to pi of the sine of phi squared cosine of phi d phi. And so let's start over here with the cosine. Well, I know that the cosine, I can just integrate this. That becomes a positive sine. So this is going to be a positive sine of theta as we go from 0 to 2 pi. Sine of 2 pi is 0. Sine of 0 is 0. Because this term is going to be 0, it doesn't matter what this is over here. Everything in this term is just going to be a 0. So all of this is just going to give us 0. So let's worry about this double integral over here. Let's break this up the same way. Let's break this up into our theta, which goes from 0 to 2 pi. We've got that integrand of sine of theta squared d theta, and then we're multiplying that by, let's deal with our phi's. We're going from 0 to pi, and we've got a sine of phi cubed d phi. All right, as far as the theta goes, we can use this double angle identity, and we can call this the integral from 0 to 2 pi of 1/2 minus 1/2 of cosine of 2 theta d theta. And this is going to give us 1/2 theta. Integral of cosine is going to give us a sine, and this 2 inside of that function will make this a negative 1/4 sine of 2 theta. Taking that from 0 to 2 pi, when I plug in 2 pi, I get 1/2 times 2 pi, which is pi. Sine of 4 pi is 0. Likewise, sine of 0 is 0, and so this is just going to give us pi. Now we're multiplying this by, remembering that we are adding these. All right, so let's really just put brackets in this to show that we're adding. And now on the right-hand side, what can we do with sine of phi cubed? Well, let's break off a sine, because then we can write this as 0 to pi of sine of phi squared times sine of phi d phi. If we do that, we can call this sine of phi squared a 1 minus cosine of phi squared. In this way, we can use u substitution, and I know we're getting a little crowded down here. If we let u be equal to cosine of phi, and du be equal to negative sine of phi d phi, then we can call this the integral, and I will need more space. So this will be the integral of 1 minus u squared du. Let's pull this negative out to the front, and this is going to give us a negative u plus 1/3 u cubed. Pulling this back into terms with cosine of phi, this will give us 1/3 cosine of phi cubed minus cosine of phi as we go from 0 to pi. And plugging this in, and let's pull all of this up here. When we plug in a pi, we know that the cosine of pi is -1, and so we get 1/3 times -1 minus -1 minus the quantity. When we plug in a 0, we just get a cosine of 1, and so we get 1/3 minus 1. Well, this gives us a -1/3 plus 1 minus 1/3 plus 1, which is a 4/3. Finally, because we are multiplying the pi and the 4/3, we get 4/3 times pi, which is 4 pi over 3. And there we have it. And so again, with this last problem, we're just giving you kind of an idea of what this application might look like. So if, for example, this vector field is a velocity field describing the flow of a fluid with a certain density, then your solution, so what you got here, this 4 pi over 3, just represents that rate of the flow through the unit sphere. And again, because we talked about the orientation, this would be the outward flow through the sphere, not the inward flow. All right, finally, we have reached a special case. Now, our special cases just make our lives a whole lot easier. And we're saying the same thing here, that if we can write this as a function of x and y, or of x and z, or of y and z, either way, if we can write one of these as a function of two variables, then we can eliminate essentially our cross product. And so we are just left with this formula. And again, you will be given this formula. So you'll be given all three of these formulas on your test. So there's no need to memorize these. And so we're going to use this to again evaluate a surface integral. We're integrating the same thing. We're doing the same thing, but this new formula just takes away that cross product. And so example 7, we want to evaluate this double integral where f, our vector field, is yi plus xj plus zk, and S is the boundary of the solid region E enclosed by this paraboloid and the plane. And so this is our figure right here. And so we're going to have to break this up into two different surfaces. Because this is called a piecewise smooth surface. A piecewise smooth surface, meaning the different parts of this surface are smooth. And so S1 is going to be this paraboloid. And so let's start with S1, because this is going to be that double integral over the region S1 plus that double integral over the region S2. And so starting with S1, we've got the paraboloid Z equals 1 minus x squared minus y squared. Because Z is written as a function of x and y, we can use this formula here. And this formula states that we can simplify this double integral over the surface of the dot product of f and ds to be equal to this double integral over the domain of negative p, the partial of g with respect to x, minus q times the partial of g with respect to y, plus r over that area. And just a little note here, because we've defined z to be equal to g of some x and y, that just means that the partial of z with respect to x is the same as the partial of g with respect to x. Same with everything else here. And so now, let's just find this integrand. So we need our p, q, and r, and this comes directly from this vector field, where we have a p that's attached to our I, a q that's attached to our j, and an r that's attached to our k. And so we're going to get a negative p, which is a negative y, times the partial of g with respect to x. Let's do that on the side. The partial of g with respect to x, again, same as the partial of z with respect to x, is going to be a negative 2x. The partial derivative of g with respect to y is going to be a negative 2y. And so for this integrand over S1, we're going to have negative y times negative 2x - our q. Our q is x, times the partial of g with respect to y, which is negative 2y, plus z. Because this is our plus r, over this area. All right, now a few more things we have to do. This z is kind of a problem because we only want this to be a function of two variables because we've got two integrals. And so I can rewrite this z as, I'm given that it's 1 minus x squared minus y squared. So I'm going to rewrite this as the integral over s1 of, and let's simplify. We get negative times a negative is a positive 2xy plus 2xy. All right, that looks like a 4xy plus z, which is 1 minus x squared minus y squared. All over that area. Great, everything's in terms of x and y. And so now let's talk about this area. Now because we're talking about a function z equals something, the area I'm going to look for is the projection onto the xy plane. And I know that projection is going to look like, well, whatever happens when z is equal to 0. And so that's going to look like the circle I can get when I move that x squared and the y squared over to the other side. That's x squared plus y squared is equal to 1. Now, I've got everything in terms of x and y. Now I could set my x and y bounds, well, in terms of x and y, but it would get a little bit messy. It would involve square roots, positive and negatives. We don't want that, and so we're going to switch to polar. And when we switch to polar, we need an r value. Because the radius is 1, this is going to go from 0 to 1, and a value of theta, because we're talking about a revolution around a circle, that's going to go from 0 to 2 pi. Now the only thing we need to choose to change is our x and y. Because we're switching to polar, we know that x is equal to r cosine of theta, and y is equal to r sine of theta. And so let's rewrite all this as the integral. Now we can put in our bounds. As theta goes from 0 to 2 pi, r goes from 0 to 1. This is going to be 4 times r cosine theta times y, which is r sine of theta, plus 1 minus. Now, if I subtract an x squared minus y squared, I know that this is going to be kind of like, and I'll do this over here on the side, kind of going to be like a negative quantity x squared plus y squared, right? And if I substitute this r cosine sine, this is going to be r squared cosine of theta squared plus r squared sine of theta squared. And if I factor out a negative r squared, then I can just call that negative r squared times 1. All right, and so this is just going to leave me with a negative r squared. I'm multiplying everything by r dr d theta. Let's distribute that r. So we have the double integral from 0 to 2 pi, then from 0 to 1 of 4 times, well, this is going to be an r squared, times that r makes this an r cubed, cosine theta sine theta, plus 1, well, now that's a plus r, minus r squared becomes a minus r cubed, dr d theta. And so now we can take this integral with respect to r, and this becomes a 4r cubed becomes an r to the 4th power. Cosine theta and sine of theta are just treated as constants in this case, plus a 1/2 r squared minus a 1/4 r to the 4th power as we go from 0 to 1. This is going to give us 1 times cosine theta sine theta plus 1/2 times 1 minus 1/4. Okay, well now this is really the integral from 0 to 1 of cosine theta sine of theta plus 1/2 minus 1/4 is plus 1/4 d theta. Now, I would need to split this up in reality because I have a cosine times a sine of theta, but I really know that this is going to be u substitution. I know this u is going to be equal to sine of theta. I can make it cosine, but then I'd have a negative, and we don't need that. I know my du is going to be cosine theta d theta, and I know this is going to be an integral of u du. So when I take that integral of u du, this is just going to become a u squared over 2. And so I'm going to cut to the chase here and call this a 1/2 sine of theta squared. Just because we see this all the time, if you don't need to write this out every time and you can do that u sub in your head, please feel free to do so. And so this is going to be 1/2 sine of theta squared plus 1/4 theta as we go from 0 to 1. I'm sorry, 0 to 2 pi. Sorry if we confused anyone there. All right, plugging in 2 pi, we know the sine of 2 pi is 0. In fact, we know the sine of 0 is also 0. And so the only thing we're going to be left with is 1/4 times 2 pi, which is equal to pi over 2. So this is for S1. Now what about for S2? For S2, and let's just do this over here. We know that S2 just comes from this plane. So we've got the plane z equals 0. We know that it's the portion of the plane contained in this circle with a radius of 1. So we already found that out. Now, my question is there an easier way? Because if we use this, in this case it's kind of a shortcut for us because we don't have to take the cross product. But is there an easier way that we don't have to do all this? Well, I remember that if I have the double integral, and this goes back to our definitions here, you can find this earlier in your notes. If I have the double integral over some surface of the dot product of this vector field ds, we said that this is really equal to the double integral over that surface of the dot product of f and the normal vector ds. Now question, what is the normal vector to S2? Well, the normal vector, because, and it's actually shown on here, the normal vector is just an arrow pointing downward. Because this is the unit normal vector, our n is just equal to negative k. Right? This is just a vector pointing downward with a length of 1 unit. And so when we take that dot product of the vector field and n, well, the x and y values are just going to be 0, or rather the I and j values are just going to be 0. We're multiplying a negative 1 by the z component. And the z component is z. And so this is just going to be z times negative 1, which is negative z. And so we're going to be left with this double integral over some surface of negative z d, and you know what, I should call this a ds because I haven't quite gotten rid of the fact that we are taking a surface integral. And what's z? Well, z is just equal to 0. So this is going to become the double integral of 0, which is just 0. And that might have seemed a little bit silly because in that last problem we found that the line integral, if we just have this circle on the xy plane, is always going to be 0, but that's not always true. It really depends on what's inside of this integral. And to show you why it's equal to 0 in this case, I've actually graphed this vector field in Mathematica. So let's see what that looks like. So when I use vector plot 3D in Mathematica and I plot this vector field, this is what I get. Now it's a little bit difficult to look at right now because the arrows are so thick and I could switch that, but if I hold my cursor on this and move it around, I can more accurately see what happens, because this gets rid of those arrowheads and makes those arrow lengths a lot more consistent and thin. And so I can see what happens at z equals 0, because this is my z-axis. I know I don't have it labeled. At z equals 0, so along the xy plane, don't we see that all of these arrows are actually horizontal? When I talk about horizontal, I mean they don't have any change in z value. It kind of looks like a line if I flatten this out. And so at z equals 0, if we think about this in terms of the water flowing through a net, if my net lies along the xy plane and the water is flowing parallel to the xy plane, that water's never going to flow through the net. And that's why that surface integral is just going to be 0 for that portion. And so finally, for our final answer, we are just adding pi over 2 and 0, which is obviously just going to be pi over 2. And so this is our surface integral of that entire surface. All right, and that is it for surface integrals, which in my opinion are probably one of the most difficult concepts in this course.